Hello and welcome to another Out of Spec Reviews video. You join us at CES 2026 because we have partnered up with Texas Instruments to learn about some really cool technology. Before we get into that, to lay the stage, Out of Spec recently went to Texas to visit with TI, and we learned a little glimpse as to what's going on with their technology with automotive. Now, they are involved in so many different areas of automotive, but in that video, we focused specifically on zonal controllers and talking about really centralized compute when it comes to automotive. In this episode, we are, of course, going to be discussing that, but we are also going to be discussing a 48-volt low or medium system voltage in vehicles, some of TI's work to enable that across the auto industry, and we'll be discussing driver assistance from sensors to software and so much more. So in this video, you're going to join me for a full booth tour at CES 2026 for Texas Instruments, specifically on their automotive side. This is a company that spans across many different competencies, and of course, we are going to bring the car stuff to you guys. So join me as we interview folks from Texas Instruments and learn about so many freaking cool things when it comes to automotive technology. Hey, Mark, welcome to the channel. Thanks for taking the time.
Thanks a lot.
So, from your perspective, you're like the mastermind when it comes to like vehicle technologies that TI offers. And first of all, I think a lot of our viewers didn't know until recently that TI makes stuff beyond calculators. And it's like this insane, massive company that does everything. We are talking about two major trends with you in the auto industry, and we're going to get into the weeds and nerds, and we're going to discuss BMS technology and BMS sway and all of these things. But 48 volt is like a real tangible trend that's happening in the auto industry. We're all familiar with the car that kind of spearheaded that, but it's really happening and taking off out there. So I'd love to hear your perspective on what TI is doing to enable sort of that 48 volt, low or medium voltage architecture inside the vehicle.
Sure. So 48 volt has been talked about a lot in the industry, and we as a company have done a lot of parts for 48 volt. And I'm not going to talk about why we're moving to 48 volt. I think many companies have talked about that already.
Yeah, I'll know. Yep.
And that changed, I can say for certain that when we get to 2028, 2029, 2030, I think we're going to see more and more regions adopt 48 volts. So I think that's very true. Now, what we're showing here is a 48 volt motor, which comes off of the 48 volt vehicle that we see on the market. So this is the windshield wiper. And so the technologies that we're working on, it has to do with power delivery, load actuation. So in this case, we're showing load actuation. To drive a 48 volt motor, we need like a 48 volt motor driver.
Yes.
And so we need to also, so what we're showing here is the board is in the area that we'll see later is actually driving this motor. Now the boards also have to work at 48 volt, which means that I need to have a 48 volt infrastructure. So these are boards that we're showing that it's like a 48 volt, 1000 watt, buck converter. So again, you have to take 48 volts and down convert it to 12 volts.
Yeah, because not everything's 48 volt, of course. So, yep, that's sort of your DC to DC right there.
Yes. And we also have other versions using gallium nitride, right? So gallium nitride is a new technology, wide bandgap solution, a little bit more advanced than traditional MOSFET technology.
Yeah.
Brings us better efficiency, smaller size.
And would you say it's comparable efficiency to like silicon carbide? Or better?
I would say in certain use cases it is better. So like for higher frequency, that's where it really shines. So basically for different voltage ranges, so silicon carbide shines in like, let's say 800 volts.
Yeah, very high voltage stuff. Yeah.
48 volt GaN, it starts to be becoming a really good sweet spot for it. And so, yeah, gallium nitride is some technology that we've worked on as well inside of TI.
That's cool.
So these boards here are showing the gallium nitride devices in different power configurations, like a 600 watt GaN converter. And this is going to the 1000 watt converter. When I first started in the industry, to do 1000 watts, it was a massively huge board, but we've progressed throughout time, switching frequency, magnetic design, and gallium nitride helps us a lot, right? Because if you look at the boards that you guys have, or that you can see online, the biggest components are usually the MOSFETs that are there.
Sure, absolutely. And gallium nitride is just significantly smaller at that point.
That's correct.
And I think it's kind of cool. You need like even audio systems to be 48 volt, of course, because then you would need an even bigger buck converter at that point.
Yes. So 48 volts, we've talked about wipers. Audio is another area that we're very excited to see moving on to 48 volt. And again, that's an area where GaN can help bring your Class D efficiency up. Because we can actually have more audio inside of a car. Because, what we see at CES this year it's really less of a focus on electrification. But of course, you can't get away without talking about AI here.
Right.
But if you walk the show floor, for automotive technology, it's really the driver assist type of functionality and also infotainment.
Right.
So the number of displays in a car, the number of audio speakers, right? We were talking about my car last night.
Yep.
There's speakers in the headrest and all that stuff. Is basically, it's all immersive audio and immersive video. And so basically these gallium nitride Class C amplifiers that we have are starting to become very popular in market.
So this is obviously, we're just talking sort of power level or sort of voltage level with 48 volt.
Right.
Central compute, tying all of these things together, that's been like the second major shift that we've been discussing a lot on our channel, going from sort of, maybe edge controllers or edge processing power, bringing it into a zonal system with 1 or 2 or 3 central ECUs. You guys are showing some of that technology as well.
That's right. So I'm glad you brought that up, because I think the whole industry is talking about 48 volt, but let's go kind of look at what's under the hood.
Yeah, come on over this way, guys. We can show you this over here. So this is a really cool display, essentially of a mock car that you have. And we've got, those are literally computers that are right in there. So take a look right inside here. You can see sort of your central compute main device right there. So what is actually happening with what we're looking at here?
So if we look at the central board here, you guys have talked about this. This is what's known as a central compute unit. This is what is going to be, for this demo, is going to be handling our driver assist, like ADAS type of functionality.
Right.
So what you see here are the computers basically, recognizing objects, doing perception, handling radar data, LiDAR data, sensor fusion, all that stuff. But this is really the brain of the entire car.
Yeah. And that's the big shift that we're seeing, is taking little tiny, thousands of little brains and bringing it into one where everything can talk to each other.
Yes, and that's the whole point, right? There's all of these, what we call edge nodes, right? So older vehicles, they would have like different types of ECUs. Each ECU would have their own microcontroller. You'd have thousands of hundreds of microcontrollers in a car. But the concept is, how do I kind of start up leveling that? Because in order for us to have vehicles that you can enjoy in your video and for people to be able to afford, we've got to reduce the total electronics in the car. And so there's no better way to do that, much like in other end equipments, like either, data centers or industrial. Like, we basically are trying to up level everything and kind of try to integrate as much functionality as we can. So the overall concept that we're showing, and is basically in every single vehicle that will be on the road, is you have a central compute, and then you have these zone control modules that surround it. So there's 3 zone control boards, this one, the one on the other side, and the one in the back. So let's just call that like a left zone, a right zone, and a rear zone.
Yes.
So the idea is that you're basically distributing the load distribution, the load actuation, the network management across these 3 centralized zone boards, and then sending everything back into the central compute. Now, yes, central compute is the biggest, one of the biggest trends, but I would say that as we, we'll talk about all the different technologies in a car, right? Like radar and LiDAR and BMS and channel sounding for car access and LiDAR and camera. Like, all of this, the way that we sense the actual world, that's all evolving. And we'll talk about that later. But in order to get that data into the system, the biggest trend is, yes, the central compute. But to me, the biggest evolution is going to actually be in the network of a car.
Right. So that is a big question, because now you're starting to have to, like, CAN can't handle everything that we're trying to throw at it, but there still will be CAN, there still will be LIN, but now there's Ethernet, and Ethernet's taking a ton of load right now. What's the perception from your side about what we're going to see?
So what we already see is that Ethernet is the predominant communication protocol between these centralized boards here. The central compute, you see this blue line that kind of comes around, that represents like an Ethernet connection.
Yep.
That's our single pair Ethernet solution that's connecting the communication between these boards. But what you just referred about, like what I refer to these as edge nodes, that is what traditionally like a zone control board would communicate to, like a BMS system via CAN, or it might connect via LIN to,
like
a
simple
sensor.
Yeah, it's simple.
And then you've got like FlexRay and PSI5 and all these different protocols, right? So that's essentially what the challenge is we have these legacy protocols, which I'm not saying they're going to go away.
Right.
But we've got these legacy protocols, but I've got these advanced edge nodes out here, and I've got more data.
You've got a ton of data now with a vehicle. I mean,
Right.
thousands and thousands of pieces of information per second.
Right. And on top of that, I've also got security, right? Because I don't want someone hacking into my traction inverter.
Right.
I don't want somebody hacking into my battery or into even the central compute to go mess with things.
Right.
So legacy things like CAN or LIN, they didn't necessarily have the right bandwidth. Security is not as effective, right? We can do things at the hardware level, but if we move to things like Ethernet, that provides things like MaxSec or max security, or also from a software perspective, right? There's a reason why servers use full Ethernet, because you can just effectively pipe data through. So when I've got radar data coming, for example, coming in, if I'm sending Ethernet packets into the zone board, I can effectively upforward it into like a switch matrix and then send it into the central compute.
Right.
Even things like audio, right? That's a form of data. We talked about it there for amplification.
And high power.
Yeah, it is high power, but that is also another form of data or network optimization. And a lot of people don't think about that.
Yeah.
Because traditionally what I have is maybe the head unit in my car has, wiring to the amplifier.
Correct.
But that's separate from all of this stuff. So really the other, major incentive for the industry is to reduce vehicle wiring. Because remember, you have all these harnesses in a car.
Right.
And so how do I reduce all that stuff? If I can go to a single communication line, it's easier. So with audio,
each zonal controller would have to handle different audio system.
right?
Yeah.
So again, in the old way of doing it, the head unit would connect to all these various speakers. You have this rat's nest of cabling to the speakers and the amplifiers. What we're doing here is basically streaming audio. Like, let's say this is our audio source. The audio data is actually going around the entire system via Ethernet, which is new in itself, right? You're sending the audio data across these blue lines. And basically the challenge, as you mentioned, is to synchronize that audio data, because this zone here is playing the speaker here.
Right.
And the rear zone is controlling those two speakers in the back.
Yep.
And the left zone is controlling the left speaker.
And that's all got to happen at vehicle startup when you're engaging driver assistance with all the signals going at the same time.
Yes. And you can imagine that if our human ear can hear the time lag that's between two speakers. So that time sync is really important.
Interesting. Now, I bet no one's ever thought of that. That is so funny. That's so great.
Yeah. That is a technology that we have enabled in our parts.
Amazing.
We can also go around if you like. We talked a lot about wiring optimization. If you kind of get around to here, so we talked about Ethernet for a bit. And again, that blue line is, let's say, like a high-speed Ethernet. That's why we're used to like 100 meg, 1 gig,
right?
Typically a 1 meg connection. When I get to my edge nodes that we'll talk about later, like the BMS and all that stuff, I don't need, or even like a headlight, I do not need to have like a 100 meg connection, because there's not a lot of data.
Of course.
So there's something the industry has introduced, which is called Ethernet 10 base T1S. It's a 10 meg protocol. Instead of 100 meg, it's a 10 meg protocol.
Interesting.
But it basically is using the whole IP tunneling or IP transport protocol. And so software becomes easier and all that stuff. But I just want to show you an example of how that type of technology, right? So in this case, we're having this zone board connected to the central compute. So central compute will say, I want to turn on the light.
Right.
And so the Ethernet 10 base T1S technology is this here. So you can do this.
Really, that's it right there. Okay.
And that is basically power and ground.
Amazing.
So in a traditional headlight, if we just look here, let's just imagine you're gonna have like a high beam, a low beam. You're gonna have motor control to kind of level. So you can imagine how, like, if that harness back there in a traditional headlight, you'd have upwards of 12, 14, 16 cables that run.
Yeah, you could see headlights that have like that twist lock connection on them with like 50 cables coming out of them.
Right. So this technology not only enables a very simplified connection over here, but it also enables what we call the remote control edge.
Right.
Because now it's saying turn on and off. In the past, like when I would have 12 wires coming in here, I would have a board that has its own MCU. It has a CAN transceiver. It has power. It has ground. It has a whole bunch of chips on there.
Yeah.
In this case, because I have a simple wire coming in, I have a one part that receives that data, and maybe like a simple driver that says turn on the light and turn off the light, because I have all the data streaming over that 10 base.
It's super cool. We actually have a whole video discussing that technology on this channel. I'll leave it linked in the description below. And it really gets into all of that technology.
And it's very similar, right? So there's, as I mentioned, Ethernet will not be the end all be all, because you're going to continue to have traditional like CAN and LIN and all that stuff. So this is, I won't talk about it too much, but CAN FD NCAN light. It's the same principle of this remote control edge.
Right.
But here we're controlling a blower, and you can see the same concept of I am simply controlling this blower fan via a single, very simplified connection.
Right.
So the way that we deal with networking, the way that we deal with wiring, in addition to the way that we're dealing with power, is fundamentally what's shaping the vehicles of 2028 and beyond.
Yeah, it's really cool to see all of this work together. Now, I want to talk to you also about access control into a vehicle.
Sure.
So we've been, phone as a key, for example, is like the #1 most requested technology, just more accurate stuff. But there's many different ways to do this. There's ultra wideband, but you had mentioned that Bluetooth low energy actually could work really well.
Yes. So if we look at car access, right? We're all familiar with our key fobs and more advanced cars have like kind of ranging technology so that it knows when you're approaching the car. As vehicles become more advanced, we're going to see models that have like, okay, I know that Kyle's getting to like 10 meters closer and
Right.
I'm going to start displaying a path with lighting. We need better ranging technology, and there has been various ways to solve that, right? Bluetooth has traditionally always been used in our key fobs.
Yeah.
So we unlock and unlock. That's for our pets.
I want to show everyone this over here, of course. We found ourselves a nice backdrop. Okay, so back to the conversation on Bluetooth low energy.
Right. So Bluetooth is not new to vehicles. When we use our key fobs to lock and unlock, right, we all have Bluetooth transceivers in our key fob as well as located on the, let's say, four corners of the car.
Yes.
More advanced vehicles have ranging technology because ranging, I can do different cool things. Like I can turn on the lights when I'm a certain distance away. Obviously, there's technology which will come on the road, which require more accurate type of ranging. And so what the industry has done, they've used different technologies because Bluetooth isn't necessarily great at ranging.
Right.
And so basically they've added things like UWB or ultra wideband. And so in those types of cars, you'll have like 4 Bluetooth transceivers, let's say on the roof. And then you're going to have like one extra UWB or ultra wideband transceivers. That's 5 different transceivers that you have.
Right.
Channel sounding is a new technology that is an open standard on the market right now. It's basically based on Bluetooth 6 protocol. It's Bluetooth low energy. It basically is equivalent to saying I can take all of the 4 Bluetooth transceivers there plus the UWB and go completely to maybe 3 or 4 of these devices. So I'm simplifying the network. I'm making it smaller in size. And I'm having performance be just good enough so that what I need in a car, I can get the right ranging and power and all that stuff.
Which is amazing.
Yeah, because phantom draw, the simplification of networking and all that stuff is really important. So what we see here is essentially the channel sounding device that we have. Basically the wireless device. This will go into our key fob, and there will also be another a board that's going to be on the car by itself. Incidentally, I'll just come back to the whole overall networking point. This is a technology where it will continue to use CAN, right? So if you imagine in here, I'm going to have a CAN bus that runs back to that the zone control board, right? I wouldn't use this. I wouldn't run Ethernet over there. That's why you're never going to have, a unified network like that. So again, I come back to that challenge of I've got so much data, whether it's wireless, or whether maybe that wireless needs to get into central compute. I have so many different protocols. I need to be able to efficiently, securely, and safely get that data back into the central nodes. So yes, this is the technology we're showing for car access.
Okay, that's cool. But I think our audience, obviously, a lot of them are EV nerds per se. You're an EV driver as well. I would love to learn a little bit more about your battery management technology.
Yeah.
And we're clearing out an area so we can make our way over this way. So let's jump over here because you have wired and wireless BMS technologies.
Yes. So maybe we can start on the other side first. We'll start here. This is a really popular part of the show. So battery management is one of the most important aspects of what we do inside of TI because obviously the battery is the most expensive component of the car.
Yes.
And it's also the most dangerous component that you have. In those 2 respects, we're working on technologies that have like battery monitoring. And our latest battery monitoring devices, have best in class accuracy. They have high channel count, so I can use as few devices as possible.
Yeah.
So you kind of have this chain of events that everything is so dependent upon how you monitor and manage the battery. So we are introducing a new technology, which is called electrochemical impedance spectroscopy.
Yeah.
It's a a mouthful.
Long one. Zoom in up on that because that's a long one to remember.
So this is a really, really cool technology, right?
Yeah.
So EIS essentially is, I think your viewers are very familiar with basically SOC. And SOC is measured by, as we talked about, is measuring voltage of the cells, voltage of the pack, current, and temperature.
Right.
So when I have those three variables, the OEMs can run their own software algorithms using those three inputs to calculate and estimate an SOC.
Right.
EIS is a little bit different approach because in addition to having those voltage, current, and temperature numbers, I'm able to extract the impedance of the battery.
Yeah. So how does it do that?
So it gets a little bit complicated. What we're effectively doing, if you want to zoom in here, is we are basically injecting a frequency or a sine wave into the battery cells.
Right.
And when we inject the sine wave into cells, we're actually exciting them, and we're looking for the response. And so the response, we run a bunch of, let's say FFTs or fast Fourier transforms inside of our chip. And so these chips in there have like advanced digital algorithms to actually take that from a time domain, like what we see in the real world, into a frequency domain.
Yeah.
And basically the computer, right? It could be central compute. It could be your main MCU for the battery management. It basically then tries to run an algorithm to say, what does that impedance translate into an actual SOC? So it's very similar to the older way of doing it, which is like I take VI and T and I run an algorithm on those.
Right.
Now I'm taking the impedance value and trying to run an algorithm on top of it. Now, I can't get away from the show without talking about AI because that is one area where when I have all this impedance data, I have big data to say across all the different packs that I have deployed across the world, across every single region and altitude and all that stuff. I can see what the impedance change correlates to. Is it a thermal runaway event? Is it, degradation event, et cetera, et cetera.
Right. But this is really cool because, just to bring it to the consumer, we discuss a lot, especially with LFP chemistry becoming so prevalent, just monitoring state of charge.
Yeah.
And so a lot of users will full charge their LFPs, or at least instructed to on their display to reset the coolant counter, if you will. But even like we were discussing, that's not 100% of the battery.
Yes. So, so you guys have talked about this before, but in order for an SOC algorithm, then in the very traditional way, I have voltage, current, and temperature. And I'm also running in the background, I have like Coulomb counters and all this stuff, right? So the OEM is going to run these algorithms to determine the SOC.
Yes.
Like you said, the battery pack, not the battery cells, the battery pack itself has to either be fully discharged, which we can't do because you'll damage the battery.
Yes.
Or it has to be fully charged. And so that's the only two ways that you're going to be able to reset the algorithm. You have to reset that Coulomb counter because you lose accuracy in that 20% to 80% range.
Yes.
So you have to get out of there in order to reset. Now, a little known fact, right? Not a lot of OEMs, I'll dare to say there's probably no OEM out there that runs the charge all the way up to the pack to 100%.
Right.
Why? Because you basically can damage the pack.
Absolutely.
So we want to basically increase the longevity of the pack, but that comes at the disadvantage of not fully resetting that Coulomb counter. It's good, but it's not.
The car never really knows what state of charge it's ever at.
And that's the point. So if you really want to know what stage of charge you're at, you would basically charge all the way up to 100% every single time.
Right.
But they don't. So they maybe give, let's say, an X% buffer in there. So if I leave like a 15% buffer, that means my SOC accuracy, based on that simple calculation, can be up to 15% less accurate than what it should be. And so if I never charge, if I'm always between 20 to 80%, I don't even know where I just get lost.
You'll lose it over time. Absolutely. And that's where we've seen cars run out with 20% state of charge or go 50 miles past zero.
So you guys have talked about this a lot, but what EIS brings is the ability I don't have to reset to that counter. So I don't run a Coulomb counter anymore. I'm using the impedance
that's wild.
actually derived. So whereas I would be up to 15% less accurate based on voltage, current, and temperature, I can be at like 3-4%, which is what we're getting right now.
Really? Wow.
Without having to reset.
And you never have to do the 100% charge.
Right. Now there's other advantages here because admittedly, using AI and all that stuff is one thing, and getting all those impedance data right across all these battery packs to extract that into an SOC.
Yeah.
I'm not saying that's a simple exercise, right? What we do is the sensing part. That's the easy part. The OEMs have the tough task of saying what happens across their battery.
Right. They've got to figure out what the data means and how to display that to the user.
But if we just talk about what additional feature, there's a lot of things that EIS brings, right? But the additional feature it brings is it actually estimates the core temperature as well. Because off of the impedance, I actually get the core temperature of the battery. Remember, in a traditional system, I'm putting like NTCs or little sensors that are like distributed every 6-7 cells.
And that's just the surface area. And it, you can't put them on every cell, of course.
Exactly. So if I have basically the core temperature, I know exactly what my temperature is. And if I even want to revert back to my Kalman filter methodology or whatever it is, my standard SOC calculation, I have a much better estimation of SOC just based on that temperature.
That is so cool. You're actually getting in-cell temperature through impedance.
And of course, thermal runaway is another big issue. When I have core temperature, I know when things are starting to run away. I know what the impedance characteristics are changing. That's why this technology, I could go on and on. That's why this technology, I firmly believe, is one of the big game changers that we're going to see.
I think we've got to do a full video on this sometime because it will change the game, especially from the EV driver perspective. This will totally make sure that you're safer and more accurate.
And we haven't even talked about charging, right? If you want to charge your battery faster,
yes,
and I want to charge deeper, right? I'm able to actually estimate and understand how much current I want to shove through the battery.
Amazing. That is so cool. I mean, there's so much stuff that you guys are doing. Just in our conversation, we've talked, sort of low, medium voltage power systems, centralized compute, access control, BMS, and we've got more to cover as well.
And I'm probably going to let my colleagues cover it, but I'll give a very brief overview.
Please,
here. We've talked a lot about BMS and car access, but on the corner there, basically is our DLP technology.
Mm-hmm.
So DLP is a technology that TI is proud to have innovated for. We see it in the theaters and know it from our projection, but little known fact, so DLP is actually used for headlight projection. It's used for interior display type is what we're showing here, like a 1080p thing, and used for like downward projection.
Yeah, so like pathway lighting,
yes.
Or like even when autonomous vehicles come or L3+, you could display like a crosswalk in front of you.
Essentially thousands of mirrors that you can kind of manipulate angles and all that stuff, but it's really the trick is the resolution that we're able to achieve. There are some OEMs out there that want to have like DLP technology for like showing projecting like full screen movies via their headlights. But I think the industry is moving it beyond that. So maybe like you're having an autonomous vehicle that has a blue light on it, like turquoise light, say I'm in autonomous mode. DLP technology, you can just say, Kyle, I see you. I'm going to present like a pathway for you to cross, right? Because having that high resolution ability to give an image across the floor is going to be instrumental. So DLP is one thing that we're excited about. Other technologies we're showing are like LiDAR. LiDAR is a big part of the show.
Yeah.
Right. So I think CES 2 years ago, we didn't see much. Last year, we saw more. As I walked the show floor, there's a lot. And I actually see a robo transport car. I think it's fully using LiDAR.
Right. Wow.
So yeah, we do see a lot of LiDAR, and TI is working on technologies that are able to drive these photodiodes. And so we're working with various other leading customers out there to, develop these op-amps and high-speed amplifiers. And
it's pretty cool. And just like sort of downsizing LiDAR and hiding them inside vehicles.
Yes,
and as well.
It is essentially our technology is inside of a headlight, and you can see in that bottom left corner there, if you zoom in, is essentially a LiDAR module.
Yeah.
So this LiDAR module is created by our partner, which is SILC. And this is basically a very smart mounting of LiDAR, because usually you see the LiDAR mounted in the corners of the car, the side mirrors, or the top, or whatever. Of course, different types of technologies for LiDAR, and that's the story for a different day.
Yeah, super cool. So we're going to talk to Keegan and Artem coming up. We're going to discuss radar technology. We're going to discuss some of the software layers that need to go in with AI control, especially when it comes to developing ADAS for vehicles.
Yeah.
But Mark, I can't thank you enough. This was really cool. I mean, I learned a ton, especially from you at dinner and here during the presentation today. Going back to so many of our viewers think Texas Instruments just make calculators. You guys are literally in almost every single vehicle on the road, maybe every single vehicle on the road. There's TI componentry,
and that's essentially our goal. Is we're trying to enable the future through our innovations in semiconductors.
Yeah, it's really awesome. So thanks for taking the time. Really great to meet you this trip. And let's go chat with Keegan.
Thanks.
Keegan, welcome to the channel.
Hi, thank you.
So we had dinner last night and we were nerding out about radars and a bunch of other stuff. And you are like insanely knowledgeable when it comes to especially radar technology.
Yes.
And I would love to learn in this segment of the video with you, but also learn about some of the products that you guys have come out with at TI. And you've got some really crazy stuff. Maybe you can start by sharing just like what radar used to look like in a vehicle.
Yeah, sure. Yeah, so radar has kind of gone on this journey. over the past couple of years. I mean, it started like getting into cars maybe 2 to 3 decades ago.
Yeah.
And there was, where it's really been has been these like very complex systems where you've had multiple chips, very complicated design. You've got separate devices that are used for like clock synthesis, and you've got power amplifiers, and you've got low noise amplifiers for your receivers, and you've got separate MCUs that are controlling for like safety in the system, and then you've got processors on board.
So like cost, weight, just like wiring going everywhere.
Yeah, also just complexity for design. These are just like these very complicated systems that requires like, you know, these armies of PhDs to be able to make happen. And really our vision when we entered the market about a decade ago was like, how can we make this simpler? How can we kind of, the term we've always used is like democratize radar and really make it simpler for deployment, and also make this technology that we really believe in brings a lot of value in terms of like robustness for the environment, bringing better resolution. There's a lot of like from blind spots or safety features that cameras can't quite cover, especially for like situations like fog or blinding sunlight, that we see that radar can really add value, and OEMs and our customers really see it as a way to add additional modalities to be able to bring in more safety, more redundancy into their system. So for us, bringing radar to an easier level to use has been a big part of it.
Right.
And so what we're showing today is the 2188. So this is an 8x8 transceiver device that essentially combines like all those different chips I talked about, from the front end and the analog to some of the digital components. It brings it onto a single device.
It brings it onto that, which is crazy.
Onto this chip.
Yeah.
So
if we were to do something like this, I know it wouldn't even be possible 20 years ago, but how big would that system have been?
It's, oh gosh, I mean, it would have been like the size of a briefcase.
Yeah,
you know,
crazy.
it would have been massive. And now you're looking at something that's the size of a cart.
Right.
Right.
It's crazy.
It's amazing.
Yeah.
And what's so great about that is it's been able to bring down not only the complexity, but also the cost of these systems.
Right.
So what's interesting about this is an 8 transmitter, 8 receiver system. And
Which
so,
is super high def. So that's literally 8 points looking out and getting back, right?
So the way you can think about it is like it's the number of transmitters multiplied by the number of receivers, essentially gets you like your number of pixels. You can think of it as like kind of your pixels. So 8x8 is essentially like 64 virtual channels that you can spread out in like horizontal resolution, vertical, and you can start to get more resolution of your scene. And so like the typical systems have been maybe 3x4. So you think of it as having 12 virtual antennas versus now this is bringing 64. So it's essentially multiplying up the number of resolution by 5.
And what would be the benefit? Would it be like lane detection for each vehicle? So if you're getting a signal back, you can accurately say, okay, that's not in my path, or is that the idea?
Yeah, we see a few cases for it. One, it's like adding more resolution gives, you'll hear like this buzzword come around 4D radar. Yeah. Essentially, it's adding a fourth dimension where most of the resolution in the past has been like kind of broadcast around the azimuth or the horizontal to be able to get things like lane separation. And now it's starting to add more resolution to the vertical to make better and more intelligent decisions around like, okay, am I going under an overpass? Am I in a tunnel? And still be able to hold resolution even in those kinds of scenarios.
Okay.
So that's one. And then also is just being able to get much longer distance. When you start adding more channels, you get more gain from your system, you get better SNR, and you start being able to detect cars at much larger distances. So especially as you're operating at highway speeds, it allows these systems to be able to take in all that data and make decisions and perceive that faster, and ultimately be a safer experience for the driver.
And ultimately, it's up to the automaker, of course, to decide how they want to integrate this into the vehicle, whether it's in the future segment of this video, we're going to talk about your own sort of central compute and AI process. But you have 2 versions you were telling me about this chip, about how it could integrate into an automaker's vehicle.
That's right. Yeah. So this is one topology that we have here that we see that's becoming very common, called a satellite topology. So what radars have typically looked like is where the processing has been at the system edge, where it's actually been at the radar sensor itself, and maybe a decision maybe made at the radar sensor itself. They determine, okay, there's a car. They may even classify.
Right, that was crazy to me that you can actually do classification on the chip before you get to a central compute, or I guess a domain controller at that point.
But now our systems have gotten a lot more complex, and as you look at level 3 autonomy, as you start looking at like these very dense urban environments as well, you start wanting to get views and visibility across the entire vehicle, and you want to understand, okay, what is one radar looking at, and being able to compare that with another. And you want to get a kind of a wider field of view around the entire car. And this is where we see a satellite topology comes in, because essentially what it's doing is it's moving the compute off of the edge, and it's taking it out into like a centralized processor that may also be combining inputs from cameras, from LiDARs and things like that, maybe running some level of fusion. but it's taking all that and trying to build a more cohesive picture around what's happening around the car.
And that's certainly the trend we've seen in the auto industry happening in the last 3 to 5 years is, taking all of the little, edge processing and bringing it into one spot. It helps with the over-the-air updates, so many millions of benefits that we've spent a lot of time talking about. But it's cool that you can offer the sensor in both versions.
That's right. Yeah, it simplifies the kind of user experience, but it also starts to improve the cost structure of these as well, because you start thinking about, okay, instead of having kind of a processor at each of the, in many cases, 5 or even 7 radars across the vehicle, you can start to consolidate that. So you can make the edges a lot simpler, and then you can just start beefing up the amount of processing that you have in the central or the domain controller.
Now, would there ever be a benefit, just for my own curiosity, about putting multiple radar, 2188s on chips? Like, let's say you wanted to have one facing one direction, one the other, or can you stack them, or how would that work?
Yeah, so another topology that we see that's very common is being able to do what we call cascade radar. So this is an example that we have from one of our partners that essentially takes 2 8x8 radars.
And that's what these are right here, right?
Yes, these are our 2 2188 sensors.
Yeah.
And so it's essentially taking 2 of these, it's synchronizing them over a very high speed 20 gigahertz link. And you can see these are actually the launch antennas that are here on there. And it is essentially building up now, instead of an 8x8 system, you have a 16x16.
Right. That's so cool. I mean, people don't realize how small radar has gotten. It's like the size of my thumb.
Right, right.
That's insane.
So now,
that's it right there.
So now you're getting to a LiDAR-like performance in radar, right? And so you're getting a lot of the benefits that radar provides around the robustness in the environment, the range that you get, and even more importantly, the cost point. Within the radar system, and you're getting to now again that LiDAR-like performance. So it's really an exciting place, and I think there's a lot of development that's really happening in the radar space, and ultimately that's helping, our customers and the OEMs to make more powerful systems to enable some of those next levels of autonomy, moving up to level 3 and beyond. And we're excited to have radar part of it.
It's so cool. I mean, we chatted last night a lot about benefits, detractions, things like that, but it really seems like many automakers, almost all of them, will incorporate radar in their vehicles.
Yeah, absolutely.
But there's also different types of radar. I don't know if now's the best time to talk about it, but maybe some in-cabin radar we can just touch on real quick.
Yeah.
If you don't mind, because this is something that we've seen pop up in multiple vehicles while we're on the topic, where you can have object or child left behind detection or animal detection. Yeah,
so this has been kind of an interesting and really developing market after over the past couple of years, where we're seeing that radar is starting to kind of proliferate into a number of different types of use cases in the vehicle. It's not just for ADAS and safety, it's also for things like in-cabin detection. We're also seeing it being used for like kick to open. We also see it being used in like some high-end vehicles for like it's embedded in the doors and it's being detecting if like preventing door dings, essentially.
Yeah, especially with power doors coming in to a lotot of cars.
Exactly.
Okay, interesting.
So, and this is one example of that, where this is a 60 gigahertz radar. This is called the 6844. It's a 4x4 radar. And this is actually an SoC in which all the digital processing for the system is embedded on board. But put that aside, what this is enabling for the end user is a lot of new and exciting applications that are inside the vehicle. And some of them are like things like child presence detection. But a big one that a lot of our customers are excited about is they see kind of the interior landscape, let's say, from a sensing perspective, and it's incredibly complex.
Oh, yeah.
Right. So if you look at a lot of the systems that are going on for airbag classification, for intrusion monitoring, for seatbelt detection, they use ultrasonic, they use these air weight, these like bladder sensors, they use these like strain gauge sensors as well for weight. And what we can do is essentially replace all of that with a single radar.
Right, it just takes so much complexity out of the rest of the entire car.
Exactly.
And you're just like, boop, look at it.
Yeah, so the radar, what it can do is it's really good at detecting motion. And so what's primarily been used for is like child left behind detection, preventing hot car deaths, for children. But we're also starting to see it now come into play with some of the power levels that we can reach. It can now start to replace the ultrasonic sensors for like intrusion sensing in the same sensor.
Yeah.
And it can be used for things like seatbelt reminder, even classification for occupants for like airbag.
Right.
warnings.
That way you can tell if, someone's got a child in a place they shouldn't be, for example, not to fire the airbag at full force.
Right.
Or something.
Right.
Yeah.
So it's again replacing a lot of that complexity that was in the system. That was in the systems today. It's being able to do that at a much lower cost point, but also adding additional capabilities that weren't there, like those bench levels of classification I mentioned.
It's pretty cool what's happening. I mean, obviously this was just my own little interest on the inside, but this is a real product that can save lives, as is this, because the time that it takes to develop a system when you have the extra viewpoint of this high definition radar? Is it technically, maybe you can answer this as well. High definition radar sounds like kind of a buzzword term, but it doesn't really mean anything.
Yeah, it kind of is. The way the market is always kind of defined is like anything beyond like 48 virtual channels, like a 6x8, kind of is considered a high definition or an imaging radar or a 4D radar. It's enough channels to be able to start allocating more of those to the elevation dimension.
Got it, understood. But it's so cool how you can, basically speed up the time of development of ADAS systems with extra sensors like this, and get to ultimately all the end user cares about is safety and usability and function. And you can do that a lot faster when you have extra sensors like this. For many automakers, almost all of them around the world are doing something like this.
Exactly. One more thing I want to kind of call out here is another technology that we have here that TI was a pioneer of. It's called launch-on-package technology, where essentially if you looked at kind of designs in the past, and we've got an example here, where a lot of the antennas that have been used have been based on PCBs. So you're essentially, you have electrical connection onto a PCB, you're transmitting a very high frequency, or you're receiving a very high frequency over like a strip line and to a PCB antenna.
Right.
And these kinds of boards, like they actually use like these very complex like PCB technologies. They're they're ceramic based. They have like these, they're very expensive.
So they're super hard to make then.
Yeah. And what we're essentially trying to do, I mentioned like democratizing, radar.
Yeah.
And so like with this launch on package, this is just a simple FR4 based PCB now.
Right.
And the this device, this is actually kind of an air interface.
Oh, really?
In which you're transmitting into essentially like a waveguide that is built into just this PCB, and this is a plastic antenna.
Oh, no way.
Yes.
Can I feel that real quick?
Yeah. So
super
lightweight.
No way.
Right?
I thought it was like copper.
No, it looks like it. It looks cool, but no, it's just a piece of plastic.
Oh, wow.
But this like then propagates into the kind of antenna design that would be used for the system.
How about that?
Right. And so what's cool about this is now a tier one or a developer for this can develop one board, and they can then develop multiple antennas.
Right.
And so if they want to deploy this into the front for something that has a very tight field of view, very long range, they could have one antenna, slap it on.
Right.
If they want to develop for a front corner that has certain requisites,
change
or
the
rear
idea.
corner for like a blind spot monitor, they can just stop on. So it just reduces complexity.
So cool.
It makes this just a more accessible and attainable.
Dang, that's really a neat piece of technology. Well, Keegan, thank you so much. I told the audience we were going to learn a lot from you, and we did. And I feel like we've got to do more on this. I really, we spoke a lot about just like testing radar systems, seeing how they work in crazy environments, and that's the major benefit here is, anything can happen on the road, and the car's got to be protected for it. So your team's doing awesome work to make this, way better for the auto industry, way more accessible, way more precise in picking up different objects. So thanks for all of that.
Yeah, absolutely. Thank you.
Thanks, Keegan. That was a great series. That was awesome.
Appreciate it. Thanks.
Well, guys, it's time to talk about central compute, especially when it comes to ADAS. This is Artem. Welcome to the channel.
Appreciate it, Kyle. Super excited to be here. Looking forward to telling you about some of the coolest things we're working on at CES this year, which is really about simplifying the experience for our customers, right? We are a large supplier in the automotive industry. Our customers depend on us. We want to make their lives easier.
Yes. Yeah. And what's really cool, we were just discussing, we're going to do this whole cool demo today where we're going to talk about radar and other sensors. But that's just raw data.
Just raw data.
So what do you do with all of that data?
Yeah, funny enough, that's the central compute, right? So you got to bring in all the data, you got to bring in all the sensors, you got to analyze them, but then you got to take it one step further and act on it, right? You got to make some decisions, and that's where the AI part in the central compute kind of comes in, right? Now we're not just telling the driver, hey, there's an accident ahead of you. Now we're stopping to make sure that you don't run into the accident. And that's a whole new bar of innovation, both from the simplification, from safety, right? But just from general performance compute, you need more and more. And quite frankly, the cars aren't getting any bigger unless you're in Texas when we're there. But everywhere else, they're not getting bigger. And so you don't have the space to start putting large chips with liquid cooling and things like that. You got to compress that into a small package, and that's what we do.
Yeah, I mean, power consumption becomes a huge figure, especially as cars get more efficient. Space, like you mentioned, and just right-sizing the sort of processing power on the vehicle for the application.
Exactly.
I think we see a lot of cars launching with big stats, big numbers, and they use 10% of their capabilities, which is not efficient at all.
Absolutely.
Yeah.
In worst case, it's launching for a $100,000 car. How many of those are being sold, right? And
exactly.
the $20,000 cars aren't gaining the technology. And that's really where TI comes in, right? We're about bringing the technology to the masses, right? And making sure that it's accessible.
So tell us what we have here. We've got some cool stuff. There is a board that is kind of running everything. Can we show that?
Yeah, absolutely.
Yeah,
if you want to kind of zoom in on a little bit here.
Take a look at this.
So we're kind of showing two things here, and we'll look at more of these demos, but effectively what we're doing is we have a hardware ECU doing cluster and parking, and then we have a virtual ECU doing driving. And what we're trying to show here is what happens in the car now, right, is our customers have to write more and more software than they've ever had before, because the cars are easier to use for us. You press a button, it parks. But for the engineer, that was a real complex problem to go solve.
A lot of testing.
Millions of lines of code to go right. And so what we're doing is really kind of you've heard the shift left software development terminology. That's ultimately what we're doing. We're enabling the software developers to start long before they've made hardware, they have a test car. There's many months before that they could be writing software. And with a virtual ECU, you can do that. And what this really means is you have the whole chip simulated in a laptop. Right. So sitting at your desk, you're writing code as if you're working on the board, except you don't have to go and deploy it to a car every day to test how it did on the road.
Right. So like the time to getting the software ready is drastically reduced.
Which is needed to counteract the fact that now we're writing drastically more software than we ever have before. And so this kind of paradigm shift is really what's really solving a lot of customers' problems. And we're doing that as part of our new generation platform. We're launching our 5th generation of our ADAS technology with a safety-enabled, high quality. It really is intended for what you would expect out of a high-quality car.
And what would you say that this helps in terms of updates to vehicles? We see a lot of cars get over-the-air updates deployed to them. I would imagine this type of technology can reduce the time it takes to validate a software update.
Absolutely. You're spot on, right? So now we're having all the cool features in the car. You got the nice cluster. Your kids in the back are watching Netflix. Let's say an automotive maker wants to release an update. You don't want the update to your IVI or infotainment system to suddenly break your braking system, right? And so customers have to go through a very long validation cycle in software classically, because they literally have to put a car on the road and drive millions of miles. That's not efficient if you're trying to do OTA once a week, right? That doesn't work that way. And so what this enables you is to actually be able to validate all your software, right, in multiple simulated chips, simulated ECUs for a much faster experience, because I mentioned it can run on a laptop, but you can also run it in the cloud and run, thousands of instances in a second, what in the physical world would have taken you a month to test.
Right. That is so cool. I mean, just the rapid speed up of development of these products, the cars especially, is crazy. And you need tech like this to get things done way quicker.
Absolutely.
Yeah.
I mean, you'll see a lot of cool technology here, obviously, for automotive, but you always have to intertwine a little bit of safety into it, right?
Yeah.
And that's kind of where these kind of tools and technology from TI come in, right, in partnership with Synopsys, that enables us to enable customers, right, to solve these problems in a safe way and do it more rapidly than ever done before.
So just on the last point, we've discussed a lot about what the automaker benefit would be to something like this, rapid time for development, things like that. From the end user perspective, let's say someone purchases a vehicle with this, what would you say is the user experience to having a car run on a platform like this?
Yeah, that's the beauty of it. The experience you want to have is frictionless. You don't want the end customer, like me, when I buy a car, I don't want to think about anything in my car. I want to get in my seat and everything works. Right? The car does what you expect it to do. It parks when it needs to park. It stops when it needs to stop. So it's actually funny. What we're trying to do is make the consumer not think about the car. Right?
Exactly.
You just get in and it does it.
The most annoying thing is like bugs and weird oddities and
flashes.
And for many more automakers who may not have gone through the insane development time to develop their own vertical stack, this can just get people right up to speed.
Exactly.
Plug and play and then develop their software off of this.
And then have that continuous innovation, right? Because in this industry, you don't stop when you release it. That's the beginning of the journey, right? Now you got to get all the OTA updates, the latest features, the coolest things. And that's where software doesn't stop.
Right.
Hardware, it stops because once you bought the car, you have it. You physically have it.
Yes.
But the software doesn't stop. It continues to evolve. It continues to innovate. Continues to deploy to you, and that's why it's so important.
Yeah, and that is clearly the consumer expectation
Absolutely.
these days is over-the-air updates and
Oh,
improvements.
yeah, absolutely. Cell phones have spoiled all of us. We want that experience everywhere else, right?
Yeah, absolutely.
You want it to just work. You don't want to have friction, right?
Yeah.
So, and that's pretty exciting, I think, on what we've been able to enable to our customers here.
Yep, super cool. Well, thanks for the time, Artem. I appreciate this demo.
I appreciate it.
I think I would love to play around with this one day, get the actual ECU
Oh, if
on
you'd
the
love it,
laptop.
we'd actually walk you through it if you'd love to. We'll get you and an engineer in a room. We'll show you exactly how it goes.
That would actually be
by
really
all
fun.
means, please come on by. We got it. And that's the extension we give to all of our customers. Anybody who wants to see this technology real, it's available. It's on TI.com. You can actually just download it and get going.
Oh, that's awesome. And the link will be in the description to it, of course.
I appreciate
Thanks,
it.
Artem.
Thanks, Kyle. It was a pleasure talking to you.
Same here. Really appreciate it.
Thank you.